Hello friends, Agrawal is Assistant Professor in Civil Department, Sandipani Technical Campus, Alapur. Today's topic is find slope at support and maximum deflection of a simply supported beam subjected to partial wear by Eclipse method. Learning outcomes. After watching this video, student will be able to understand the concept of Eclipse method, and also student will be able to find the slope and deflection of a simply supported beam subjected to partial UDL. Now this is our example here. This simply supported beam subjected to partial UDL and of intensity is 30 kN per meter. So find slope at A and maximum deflection of a beam. So first step is to find here the reaction. So we take here sigma EMA is equal to 0. So we are considering clockwise as positive and anti-clockwise as negative. So we can say that here we are taking moment about this A. So this 30 into 2 is a force clockwise. So 30 into 2 into half distance 1. Then this is minus, so minus 6 RB is equal to 0. So we got here the RB is equal to 10 kN. Now if you apply sigma Fy condition is equal to the 0, so vertically upward is plus and vertically downward is the minus. So this we can say that RA is vertically upward, we are assuming, then plus the RB, and this load is minus, so minus 30 into 2 is equal to 0. So we can say that RA plus the 10 minus 30 into 2 is equal to 0. So we got here this RA is equal to the 50. So RA is the 50 kN and RB is the 10 kN. Now when the beam is subjected to partial UDL, we have to modify this beam. We have to always apply the UDL throughout the length. So here applied load is a partially. So here we have to make some changes in the beam. So this beam is to modify like this. Now here the previous load is up to 2 meter. This is a 30 kN per meter. So here again we have to apply the UDL throughout the length. So the remaining length also we have to apply the load, and the intensity is the same, that is the 30. But here we have to again apply the reverse load, so that nullify this previous load. So again we have to apply here the vertically upward UDL. So that this UDL will nullify the which is load we have extended, this UDL, that will get the nullify. We know this length is a 2 meter and this length is a 4 meter. Now here we know EI d2y by dx square is equal to the mx. So now for the Eclipse method we have to apply the sections. So here we are going to apply the sections. So this is a first section, and here from this length, after this 2 meter, the load has to be changed. So here we have to again apply the section. So this is the second section. Section 2. Now this is, we know, is a 50 kilonewton and this is a 10 kilonewton. So mx, that is the bending moment. So we know this for this section, this is now our x. So we can say that is 50 into the x is create the sagging bending moment. Then this UDL is create the hugging bending moment. So minus 30 into x by 2, that is x square by 2. This is the first section. So again draw one vertical line, then go for the second section here. So here this UDL, this continuous UDL already count in this previous section. So only this load is to remain. So this load is create the sagging bending moments, that is why is a plus, and this UDL is a 30. So we require this length. So now for the second section, this is our x. This is our x. So this length is x. So this remaining length, this length, this length is, this total is the x, the x minus this 2. So remaining will be the x minus 2. So here we write the x minus 2 into x minus 2 divided by 2. So that becomes x minus 2 raised to power 2. So now this mx we have to put in our this derivation or equation. So we know here the EI d2y by dx square is equal to 50x minus, this becomes a 15x square, then this section is over, plus here the 15 into x minus 2 bracket square. Now next step is to integrate this. So we have to integrate both the side. So this becomes EI dy by dx is equal to, this becomes 50 x square by 2 minus here 15 x cube by 3 plus the add one constant of integration, that is section, plus the 15 x minus 2 bracket cube divided by 3. So simplify this equation. So this becomes EI dy by dx is equal to, this becomes 25 x square minus 5 x cube plus the C1, then here the section, then plus the 5 x minus 2 raised to power 3. So this is the our slope equation. Then again integrate this. So integrate this, this becomes EI y is equal to, this becomes 25 x cube by 3 minus 5x raised to power 4 by 4 plus the c1x, here integration of c1 is c1x, plus one more at the constant of integration, then the section complete, plus here 5x minus 2 raised to power 4 by 4. So now here unknown is the c1 and the c2. For that we have to apply the conditions here. When boundary condition, when x is equal to 0, so y is equal to 0. So this x is 0, it means it is limited to first section. So put here in this equation, this is a deflection equation. So 0 is equal to, here is 0, then minus here also the 0, plus the here is 0 plus c2. So we got here c2 is equal to 0. The next is we have to apply the second condition, boundary. So boundary condition, that is x is equal to the 6, y is equal to 0. It means we are putting x equal to 6, it means we are reaching the support. So here again the deflection is 0. So x is equal to 6, the y is equal to 0. So now again here put in this condition, this becomes the 0 is equal to, now here 25 into 6 raised to power 3 by 3 minus 5 into 6 raised to power 4 by 4, then plus 6 into the c1, then plus 5 by 4, here 6 minus 2 raised to power the 4. Now if you solve this equation, so here we got the value of the c1 is equal to minus 83.33. So in this way we got the value of c1 and c2. Then our aim is to find the slope at a. So slope at a. For that we have to put x is equal to the 0, this dy by dx is become the ia. So now we are putting here the equation first. This ei dy by dx is equal to 25 x square minus 5x cube plus the, here is c1, then bracket here the section, and 5x minus 2 raised to power 3. So here we have to put the value at c1 is equal to the minus 83.33, then x is equal to 0 and c2 is equal to 0. So x equal to 0 means this limited to the section. So when you put here this ei will become the ia is equal to, so x equal to 0 means this quantity and this quantity becomes the 0. So c1 is equal to the minus 83.33. So we got a value eia is equal to minus 83.33 divided by ei. So we got here the slope. So this negative sign indicates that slope is the clockwise. Now next our aim is to find the maximum deflection. So this maximum deflection is occur, maximum deflection is occur where the slope is 0. Where the slope is the 0. So now we are assuming that here, first assumption here, our assumption is maximum or slope 0 occurs between, suppose this is A, B, this is A, this is B, and this is C. So in the section BC, so if the section occurs in section BC. Now if our answer is more than the 2 meter, it means if we got the value of x is more than 2 meter, then our assumption is correct. Otherwise we have to change our assumptions. Initially we are assuming that our deflection is maximum in BC section and this 0 slope occurs in the BC section. When we are equating this slope equation equal to 0, and for the total equation, first section and total second section, if the answer is more than the 2 meter, then our assumption is the correct. So for that we have to equate, for the equating slope equation is equal to 0. So now this is BC section, so we have to use the total equation. So our slope equation is, first right here, so EI dy by dx is equal to 25u into x square minus 5u x cube. Now here minus 83.33 is the C1. Then here the section plus 5u into x minus 2 raised to power 3. Now we have to make this quantity 0. So here we have to make this quantity as 0. So we are equating 0. So this equation becomes here 25u x square. So here we are equating this slope equation equal to 0. Now this we cannot directly solve here. So here we have to find the value of x by trial and error method. Trial and error. It means we have to assume some value of x, put here equal to 0. So take the 2-3 tiles. So we got here the x is equal to 2.6332 meter. When we put value of x is equal to 2.633 meter in this equation, so that is equal to 0. So now we got the location of the maximum deflection. So location of maximum deflection is 2.6332 meter. So putting this value in deflection equation, so we got here the maximum deflection. So first we write the deflection equation here. So EI y is equal to the 25 x cube divided by 3 minus 5 x raised to power 4 divided by 4, then minus 83.33 into the x, then the section here plus 5x minus 2 raised to power 4 by 4. Here we have to put the when we are putting x is equal to the 2.6332, so this y becomes the y max. This y becomes the y max. Now EI y max is equal to 25 into 2.6332 raised to power 3 by 3 minus 5 by 4 into 2.6332, this raised to power 4 minus 83.33 into 2.6332, then plus here 5 by 4 in bracket 2.6332 minus 2 raised to power 4. So after solving this equation, we got here EI y max is equal to minus 127.16. So here y max equal to minus 127.16 divided by EI. So in this way we got here the maximum deflection. This negative indicates, negative sign indicates here the deflection is the downward. The deflection is the downward. So we can derive this equation y max equal to 127.16 divided by EI, and this is the dot. So this is the final. In this way we got the slope and deflection both when the beam is subjected to a partial UDL. Thank you.